Welcome to Lesson 8b, Fumigating Plume Approximation. Last time we had that long equation with the infinite number of image sources, which is hard to use. This time I'm going to give you an approximate analysis for this fumigating plume. And we're talking about an elevated temperature inversion with a reflecting ground, just like last time, same problem. I'm going to start with a picture that my wife took while we were driving down to Harrisburg along 322 East. I got so excited when I saw this and I said, quick, take a picture, get your cell phone out. That's a fumigating plume like I teach about. So this is a flow from right to left in this case, opposite of what we normally show. But obviously there was a lid of some sort here. So you can see this top lid of a temperature inversion. So there was a temperature inversion above there somewhere. So if you plot temperature T, it had unstable and then it turns up. And what it does up here, I don't care, because this was like a lid that fumigated everything underneath, and it's obviously also fairly unstable under the plume so that it's mixing. If this is a pure reflecting ground, which I don't know if it is or not for this particular air pollutant, but there's a lot of smoke in there too, that tends to settle down a little bit into the ground. But as an approximation, this is a real nice fumigating plume. So how do we treat this as an approximation so we don't have to use all those infinite number of image sources that we talked about? So here's what we have the setup, same as before. We have an elevated temperature inversion. Again, we don't really care what's going on up here. We have this elevated temperature inversion here that becomes a lid that traps all the air pollutants. So we have reflections going on. It reflects here at the elevated temperature inversion and it reflects from the ground. We have a reflecting ground. And so all the air pollution is trapped between the elevated temperature inversion and the ground. So our approximation, the most key one, is that it's well mixed vertically. So what that means is that we're going to take a given X location and we're saying that there was a lot of mixing going on under this. So this is probably like a class A or a class AB or B. It's an unstable situation underneath the temperature inversion. So there's a lot of mixing going on such that we will get a well-mixed situation. So what I'm going to do is plot the actual CJ as a function of Z in this case. This is looking from the side. The outer edge of our normal Gaussian plume is here and here. So our Gaussian will look something like that, like we typically have. Now what we're going to do is say all of this, everything up here is now inside the plume, and everything here, these tails are all trapped inside the plume, and we're saying it's well mixed, so there's no change in the Z direction. So we're going to replace all of that Gaussian plume with just a rectangle, and we say that the area that I'll sketch here, all of this air pollution is now in this box, where I'm going to call this CJ, comma F. Capital F is for fumigating. By the way, this is HT. So this rectangle has the same area, and this is at some X and some given Y, and you could typically, we're looking at Y at the center line here at the directly downwind, but we're going to equate those two areas. So all the air pollution from the plume, the Gaussian plume, is trapped inside there. So this makes it actually quite simple. And so all we have to do is equate these two areas. So this area that I sketched in red has to equal the box area that I sketched in blue. This one's the easiest one. This is just CJF times HT, because we have a elevation HT and we have constant CJ, we call it CJF. So that rectangle is already done. We just have to integrate this Gaussian. So we're going to integrate, not worrying about the ground or the inversion. We're just pretending we have a Gaussian plume, so we have to integrate the whole thing. So let's start, and I typed all this out so I don't make a mistake here. We start with the basic Gaussian plume model with one source and no image sources. So it's just the first one we introduced, except we modified it for the height, capital H. And what we need to do is integrate that at some X location, downwind, where everything's well mixed. All of the air pollutant is trapped between the ground and the bottom of the elevated temperature inversion. So we know that. So we're going to integrate over Z to get the mass per unit area at some X and Y location. So again, this is just a slice. So instead of CJ being a mass per volume that we're integrating, it's a mass per area in this the areas here. But when we actually calculate CJF, you can think about a unit distance in the y direction to make that a volume, but we can leave that out for now to do our algebra. So we integrate over z to get the mass per unit area at some x and y location. So we're going to integrate from -infinity to infinity over z. Why? Because it's a Gaussian and this extends to infinity up and down. And then we're going to put in our equation. So we just put this equation into here times dz and equate that to CJF HT. Here's what we can do to simplify this. And that is first that everything here, all of this, is not a function of z. There's no z in any of that. So we can move that outside of the integral. And so when we rearrange, we get that whole term. I've also moved the sigma z into the integral, or left that in the integral, I should say. So the sigma z is still there. And I split the 2 pi into a square root of 2 pi there and a square root of 2 pi there. The reason I did that was because if you rearrange it this way, with the sigma z in the denominator inside the integral, square root of 2 pi there, but everything else outside, all of this is just not a function of z, so we have all that out. And if you get a math book out or look it up on the internet, when you do the variable transformation from z to some other variable, and you have the sigma z in the denominator and you have another one there, and you do the transformation, you will find that this integral from -infinity to infinity, by definition of a Gaussian, this whole thing in red is equal to 1. You can look that up and verify that. That makes us very happy because that whole entire term goes away. And so now we get CJF by dividing by HT, and we have this final equation for a well-mixed. This is an approximation now. This is our approximation for a Gaussian plume with reflecting ground, elevated temperature inversion. The only restriction here is that the elevated temperature inversion bottom is at HT. HT has to be bigger than H as we sketch, so that the entire plume is underneath that temperature inversion and it's trapped there. And we made the well-mixed assumption, and it's fumigating, and this is our final equation, nice and simple. And so that's all we have. So let me make a couple comments about this. First of all, CJF is equal to CJF of x and y only. We've gotten rid of z, so z dropped out, which we would expect because we are assuming well mixed. So what that means, remember we did flux chambers and stuff with well mixed. So that means if you're sampling this anywhere in the z direction, it's the same CJ everywhere at this particular x. At a different x, it's going to vary. It's going to obviously decay. CJ is going to decay with x. So this CJF is only a function of x and y. It is an approximation because it's not going to be perfectly well mixed, but as long as you go far enough downstream, it should be okay. So that's my first comment. Another comment is that, as you see up here, CJF is a function of y. And if we are plotting this at the center line, if you go out of the page from the center line, you will have different values. You say, how does this vary with x? I don't see any x's there. The x is because sigma y is a function of x. Notice also that sigma z has dropped out very conveniently. So I'm happy about that too. Sigma z has dropped out because when you do the transformation of coordinates, that sigma z and this sigma z, when you change your dz to some d psi, or however you're going to do this, and you work through the integral, it actually just drops out completely. So we only need those coefficients a and b in the Martin model. We don't need c, d, and f to get sigma z. We don't need sigma z anymore. But CJF is a function of x because of sigma y, and it's a function of y, obviously, because of this exponential term. And so let me look at this in a little more detail, and we have to think of this three-dimensionally. So let me pause and draw some stuff here. From the top view, here's our source, and the wind's blowing from left to right. We have our Gaussian plume spreading horizontally. So if we plot CJ as a function of y, we have our standard Gaussian shape, which flattens out as you go downstream. Now this thing is spreading as you go downstream, and if we look at the total area in here, this is spreading out, and it's the same air pollution that's been there because it's trapped between the ground and the temperature inversion. And with our well-mixed approximation, if I take this center line, if I'm talking about the center line, and I take this value of CJ, it's the same value out of the page between the ground and HT, the bottom of the temperature inversion. So it's like looking from the side, you see a rectangle like we drew in this approximation. And then that rectangle, of course, that distance gets smaller as you go downstream to a different X. So let me sketch this also from the side view. From the side view, we have our plume starting at the top of the stack, but it rises due to buoyancy. So the actual center is here like we always do at capital H. And then it starts spreading out very quickly because this is an unstable atmosphere here. And then by the time it gets to X1, we have CJF at X1 and CJF at X2 when it gets down here. So this value CJF is decaying with X. And if you think about it, since everything is well mixed in the vertical direction, there's no difference between here and here in the Z direction. So if I take a slice here, it will look like a rectangle. So this is a Gaussian in Y, but it's a rectangle in Z. So imagine this Gaussian, as you go out of the page, it's just repeating that, take that and keep stamping itself on itself as you go out of the page. So you see it this way. So you have to kind of visualize that in 3D. So that's what this equation is doing. And I should mention that there's a region here where this approximation is not valid for small x, because it has to have a chance to mix well enough and to fumigate till we have this well-mixed approximation at some x location that's a little bit further downstream. You can calculate this from x equals 0 on, basically, or a little bit above 0, but you can only use it for x far downstream where it's had a chance to get well mixed, like what you saw in that first picture that I showed. With that, I'm ready to do an example problem. So here we have a buoyant plume emitting air pollution, and wow, this looks like the same plume we had previously. Yes, exactly the same plume. I just keep doing it. It's our favorite plume again. We have the same H is 100 meters. We have the same m.js as before, 110 kilogram per second. Here we have an elevated temperature inversion between 120 and 140. Well, we don't care what the 140, that could be 10,000 as far as we care. All we care about is the bottom of the temperature inversion, which is at HT, 120 meters. We have a wind speed. I did change that because I wanted to make sure that this is well mixed case, that it's mixing a lot. So if I look at these weather conditions, 1.4 meters per second, the clear summer day, 65 degrees above the horizon is the sun. This turns out in this particular case to be a class A in the Martin model, which is the most unstable. So this is going to have lots of looping. It's actually going to be a looping plume that's going to mix very rapidly. And then at some distance downstream, from there on, we'll say it's well mixed and we can use this approximation. So that's what we're doing. And it's a reflecting ground. If it wasn't a reflecting ground, you'd lose some of that like we talked about previously, but all of this pollution is trapped there. And at the center line, y equals 0, we want to find this approximate CJ at some distance. I picked 2 kilometers and just calculate that. So solution, use the Martin model, and we see that this is a class A, so we get our coefficients. All we need is A and B. We don't need C, D, F anymore since sigma Z has dropped out. So these are actually very easy.
I like it when things are easy. Yeah, Dad, we all like that.
And then we use sigma y equal AXB, and I get that sigma y is 395.822 meters in this particular case at that x of 2.0 kilometers. And then we use this equation. And at y equals 0, we have e to the 0. And if you remember from your math class, or just plug it in your calculator, e to the 0 is 1. So this whole term goes away. And so actually, all we have to do is plug our numbers into this expression to get our final result. I get 660 milligram per meter cubed to 3 significant digits. And so that's our CJF for the fumigating approximation model. Notice I used the unity conversion factor because we wanted our answer in milligram per meter cubed, and I had it in kilograms up here. The seconds cancel out and we end up with 3 meters on the bottom. The kilograms cancel out and we end up with milligram per meter cubed, which is what we want. A number of you are still having some problem with units. Always use unity conversion factors and you'll never have a problem with units. Do this in all your classes and in your life, and I can guarantee you'll thank me in the future for stressing that. So that's all there is to it. You can easily also solve this for y if we want to plot hazardous areas and stuff like that, like we did before. And this equation is actually the easiest one we've had so far with all these plumes. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.